Alrighty, this is YouTube homework 4. So the first question. A string is tied to a book and pulled lightly as shown to the right. The book remains in contact with the table and does not move. Draw a free body diagram. So as you can see here, I have, it might be a little small, but I'll spin it out. So we have the force of the book being pulled down by gravity or its weight, being pushed down towards the table. Then we have the normal force from the table pushing up on the book, and the tension by the string. And the normal force and the tension will add up to the weight here. B. How do the forces exerted on the book, in this case, compare to the forces exerted on the book when the string is not present? List any forces that are the same. Make a separate list of forces that change or are not present. So basically what happens here is the tension will be removed from this, and the normal force will now be assumed. I'll assume it's a pretty sturdy table. The normal force will now be equivalent to the force by gravity. Equal in magnitude, however, it's not the third law. It's not equal and opposite. All right, so consider the following statement made by a student about a book at rest. The two forces exerted on the book are the normal force directed up and the weight of the book directed down. These are equal and opposite to one another. By Newton's third law, they are a third law force pair. So the normal force is always equal to the weight of the book. Do you agree with the student? Explain why you agree or disagree. And here I said they are not third law forces. So from my understanding, a third law force is, for example, the weight of the book is caused by, is the force on the book by Earth, which is gravity. And the equal and opposite, or third law pair, would be the force on Earth by the book. Now while these are, so in the student's example they are equal and opposite, it is just in this context. A normal force will not always be equal and opposite to its weight, and they are not, they're different forces. The normal force is the table onto the book, and the weight is the force of Earth onto the book. So different forces. They are not a pair. All right. Consider a book on top of a level table while the book is being pressed straight down by a hand. In the space below, draw a free body diagram. So here, in this example, our normal force is going to be greater. Should be the largest force. And then we have the force on the book by gravity, or Earth, and the force on the book by the hand. So these most likely wouldn't be equal, but it works in this context, and the normal force, of course, should be equivalent to these two forces added together. How do the forces exerted on the book in this case compare to the forces exerted on the book when the hand is not pushing? So here I said, I just explained. So when the hand is pushing, the normal force is going to be larger because the book, in either scenario, whether the hand is or is not present, is going to be static. So the normal force is going to equal the weight plus any force exerted by the hand. And if you remove the hand, the normal force will then just equal the weight, or the force on the book by gravity. Is the magnitude of the weight equal to the magnitude of the normal force exerted by the table on the book? So we sort of touched on this already, but the answer to that is no. And we can tell because the book is not moving. Let's see, if the weight was equal to the normal force, then there would be a net force as a result of the hand, and it would be accelerating down through the table. A weak table, possible. All right. So let's see, on to the next page. The first question is part C. Review your answer to part A. In addition, reread the portion on blah, then consider a book on a level table. Which force completes the Newton's third law force pair with the normal force exerted on the book by the table? That would be the force exerted on the table by the book, or labeled here, force force on table by the book. Which force completes Newton's third law? Force pair with the weight of the book. So, force on Earth by the book. Let's see. Question 3. A chain is suspended by a rope as shown to the right. The chain is composed of 4 identical links and does not move. So here we're asked to draw 4 body diagrams, one for each link. And now in the first 3 links, they should all be very similar. They're all looking at essentially, they're all looking at a very similar scenario where there's a tension force upwards, which is going to equal the gravity force of the link, and a downward tension resulting from the other chains. So the magnitudes are the trickiest thing here. So for example, in diagram 1, this tension force is going to be equal to the tension of link 2 on 1 plus gravity. But what's interesting about the tension of 2 on 1 is that 2 on 1 is actually equal to the weight of 2, 3, and 4, equal and opposite of that, plus gravity. And it's a similar scenario as you go down the chain until you get to the last one where the tension between 3 and 4 is equivalent, link 3 and 4 is equivalent to the gravity exerted on the 4th and final link. So as you can see here, we were asked to, so moving on, identify all the third law force pairs in your diagram by placing one or more small x amongst the pairs. So here we have, let's see, tension exerted on link 1 by 2 is equal and opposite to 2 on 1, which is transitive, or it's comparable to what I was saying earlier, in that the upward tension is decreasing. However, I don't know where I was going with that. So you've got similar pairs in all of these scenarios. So the tension on 2 by 3 is going to be equal and opposite to 3 by 2, and 3 on 4 as 4 on 3. And as you can see, they are decreasing as they go across, just because there is less weight that these tension forces need to hold up. And that's shown most clearly in this final example, where the Newton third law pair is just equal and opposite to gravity. So rank from largest to smallest the magnitudes of all forces in your diagram. So here I said T1 by rope is going to be greater than tension of 1 by 2, which is equal to tension of 2 by 1, which is greater than, let's see, tension of 2 by 3, which is equal to tension of 3 by 2, which is going to be greater than 3 and 4 by 4 on 3, and these will be equal to the gravity of 1. So this final pair is equal to the weight of each individual link. All right. Alrighty, I had to edit a little bit, so let me cut forward here. Here we go. So now we're looking at a system which represents the first 2 links, and we're looking at its body diagram. So here we have the tension of the system against the rope, which will of course be the largest force, then the gravity exerted on the system, and the tension of the system exerted by link 3. Compare the forces that appear on your free body diagram for a system to the system to those that appear on your diagrams for links 1 and 2. So the tension on the system by the rope is actually going to be equal to the tension on link 1 by the rope. And that of course makes sense because it's holding up, this rope is still supporting the same amount of weight here. It's just we're looking at this as a unit. And that is going to be greater than the tension of link 2, or excuse me, the tension of the force on link 1 by 2. Then we're looking at gravity. So the gravity of the system, or the weight of the system, is going to be greater than that of the individual weight of link 1 or 2. And the tension on the system by link 3 should be equal to the tension of link 2 exerted by link 3. And once again, that should make sense because it's the same amount of weight being held here, which is pretty cool. I guess it makes a lot of sense. It's kind of hard for me to describe it, but it's just we're looking at the same amount of weight overall, so it's the same tension between 3 and 2, or 3 in the system. Are there any forces on your diagram for links 1 and 2 that you did not list? If so, what characteristics do these forces have in common? So we don't look at the tension on 1 by 2 and tension on 2 by 1. And what do these forces have in common that none of the others share? So they are so I guess the main thing is just that they're within the system, so I don't need to list them. The system is composed of this link, however, the system is not the link itself. And then part C, let C represent the system consisting of the whole chain. Draw and label a free body diagram for C. So here we have, so C would be the entire chain. We have tension on C by the rope and the weight of the rope itself. And this is pretty representative of our past drawings. It's just showing that the tension supports the weight of all of the chains. All right, page 4. A block is at rest on an incline as shown below at right. A hand pushes vertically downward with a constant force. The block remains at rest while on the incline. So here we got a normal force. We've got the force pushing down by the hand, force of gravity, and your static friction force. For each force that appears on your free body diagram, identify the corresponding force that completes the Newton third law. So we've got this normal force will have a normal force of the block, or excuse me, of the ramp being pushed by the block. We've got the force of the block, or the force on Earth being exerted by the block, the force of the block, the force on the hand exerted by the block, and the static friction force on the ramp exerted by the block. Suppose that the hand were to push with a constant force directed as shown to the right. The block remains at rest on the incline is the magnitude of the net force. So here we know that it is equal to, I am making the assumption that the block is not moving in either scenario. So essentially our normal force is going to be greater, and as a result our static friction force should be greater, because the static friction force is equal to mu multiplied by our normal force. And from my understanding, mu is a constant, and that means our static friction is proportional to our normal force. So our static friction will increase proportionally, which answers part 2. Person pushes a book against a wall so that the book does not move. And we actually did something just like this in class, so it's pretty cool. We've got the force on the book by the hand, which is pushing towards the wall, and the normal force on the book by the wall, which is pushing equal and opposite. Now, not a Newton third law pair, but they are equal and opposite. Then we've got the force on the book by earth or weight, and our static friction on the book by the wall. And the equal and opposite forces here. So we've got the friction of the wall by the book and the normal force on the wall by the book. The force on the earth exerted by the book. And our final third law pair is the book being pushed by the hand. The opposite is the hand pushing on the book. And that really does it. Hope you enjoyed.